So we will see few examples so that this concept is clear. First example, let us take x of t to be rect of t by 2t. Okay, so let us take x of t to be rect of t by 2t. So we already know what is the plot of this signal, correct? So it is a rectangular signal from minus t to plus t with amplitude 1. Okay, so will it satisfy, will it have average value to be 0? Definitely. Why? Limit t1 tends to infinity 1 by 2t1 integral minus t1 to plus t1 x of t dt. Let us calculate. Okay, so this should be equal to how much here? Limit t1 tends to infinity 1 by 2 t1, I'll keep it out, but the signal exists only from minus t to plus t with amplitude 1 dt. So this should be equal to limit t1 tends to infinity, you get t by t1, correct? So this integral will give you 2t divided by 2t1. So 2 will get cancelled, you will get t by capital T1. So but because t is a finite number, right? So t is a finite number and denominator is infinite, so this would be tending to 0, and hence what do we say? The average value of this signal x of t is 0, and hence I can directly differentiate this signal. So let us try to plot the derivative of this signal. Okay, so how does the derivative of this signal look? We already know wherever there is discontinuity, we have to replace that discontinuity with Dirac delta function. So you will get minus t. At minus t you will have a Dirac delta of strength 1, and again at plus t you will have a Dirac delta of strength minus 1. So this would be the derivative of x of t. Now let us apply differentiation in time domain property. Okay, so what do I mean by that? So we know that we got d by dt of x of t to be equal to how much here? This signal. How do you write this in a mathematical form? That is delta of t plus capital T, which is this positive Dirac delta, minus delta of t minus capital T, which is this negative Dirac delta. Now let us go to frequency domain. So d by dt of x of t, we know that its Fourier transform is j omega times x of j omega is equal to what property we have to use here? You know that delta of t will have what as Fourier transform 1, but it is shifted to the left by t units, and hence we have to use time shifting property, and you will get e power j omega t minus this flow will have e power minus j omega t as the Fourier transform. Okay. Yes, so this implies j omega multiplied with x of j omega would be equal to 2j. So e power j omega t minus e power minus j omega t would be 2j sine omega t, and j will get cancelled, and finally we get x of j omega to be equal to 2 sine omega t whole divided by omega, which is same as what the result what we already know, right? Fourier transform of a rectangular function is, or I'll write down nicely here, it's very cluttered. Okay, so this implies x of j omega to be equal to how much? 2 sine omega t whole divided by omega. So that would be the Fourier transform of our rectangular function. This result we already know. Okay, in that way we can use the differentiation in time domain property to find the Fourier transform of our rectangular function. Okay, now let us take one more example, which is, let us take x of t to be equal to tri of t by 2t. Okay, so it is tri of t by 2t, means we already know that triangular signal. Okay, so how does the plot look here? So from 0 to width should be 2t. Okay, we have seen this in the first chapter. Okay, what is the equation of this line? It is 1 minus t by 2t, and you have one more straight line like this from minus 2t to 0, and the equation of that line would be 1 plus t by 2t. Okay, that is our x of t, and I will leave it as homework to prove that average value of x is equal to 0. Okay, I'll put a question mark, means you have to prove that as a homework. But because its average value is 0, let us try to differentiate. We can use differentiation in time domain property, and hence let us differentiate this signal. So how does the plot of the derivative look here? Sorry, this is our x of t, correct? So if how does the derivative of this x of t look? Note that our x of t is an even signal, so definitely its derivative would be an odd function. So from minus 2t to 0, it is 1 plus t by 2t, so its derivative would be just 1 by 2t. So this is minus 2t to 0, and the amplitude would be 1 by 2t. Then from 0 to 2t, the equation of straight line is 1 minus t by 2t. So derivative of that will give you minus 1 by 2t. So it is a rectangle with negative amplitude from minus 1 by 2t, and that exists from 0 to 2t. Okay, so this would be the derivative of x of t. So let us not stop here. So let us differentiate it one more time. Okay, so then it would be easy for us. Why? If you differentiate it one more time, we get everything in terms of Dirac delta functions. Okay, so let us differentiate this signal one more time. So d square x of t by d square by dt square of x of t. So how does the plot look again? So you are differentiating this function one more time. So because there are discontinuities, those discontinuities should be replaced with the Dirac delta function. So at minus 2t, you have a Dirac delta of strength 1 by t. So from minus 2t to 0, it is 0. At 0, what is happening again? You have a discontinuity which is in negative direction. And what about the strength of Dirac delta here? It will be minus 1 by t. And again at 2t, what will happen? You have a positive Dirac delta of strength 1 by 2t. So this would be the double derivative of our original triangular signal, which is tri of t by 2t. Okay, so because that triangular function has average value to be 0, we can use differentiation in time domain property. Okay, so let us solve that here itself. So what is that we have got? D square by dt square of x of t would be equal to how much here? This fellow can be written as 1 by 2t delta of t plus 2t, correct, minus 1 by t delta of t plus 1 by 2t delta of t minus 2t, correct. So derivative of double derivative of x of t can be written like this. Why? This Dirac delta is positive, positive strength at minus 2t, and strength is 1 by 2t, and similarly this is the Dirac delta at origin with negative strength, and strength is minus 1 by t, and we have one more Dirac delta at 2t with positive strength, and strength is 1 by 2t, which is written in this form. Now let us go into frequency domain. Because you are differentiating twice, what will happen? You will get j omega whole square multiplied with x of j omega would be equal to how much here? So here which property we have to use? Shifting in time domain. So you will get 1 by 2t multiplied with this fellow will have e power j 2 omega t minus this fellow will have minus 1 by t plus 1 by 2t. This fellow will have e power minus j 2 omega t. Okay. Okay, so we can further simplify. This should be equal to how much? In first and last term, 1 by 2t is common. So you will get e power j2 omega t plus e power minus j2 omega t, which is 2 cos of 2 omega t minus 1 by t. Okay, so this 2 will get cancelled out, and finally what do we get? We'll write down that here. This implies minus j omega whole square, which is nothing but minus omega square x of j omega would be equal to, here also we can take minus 1 by t out. I will get 1 minus cos 2 omega t, which is 2 sine square omega t. Okay, okay, j omega whole square x of j omega is minus omega square x of j omega, and here we took minus 1 by t out, and we get 1 minus cos 2 omega t, which is 2 sine square omega t. So this minus will get cancelled out, and finally we get x of j omega, correct? We get x of j omega to be equal to 2 sine square of omega t divided by omega square t as the Fourier transform. This would be the Fourier transform of our triangular function. Okay, so it's up to you. So depending upon the problem, it is up to us to use how many differentiations.